Good morning, everybody. Our lecturer today is Kathleen Aviso, who is a university fellow and a professor of the Department of Chemical Engineering at De La Salle University, Manila, Philippines. She's also the current dean of the Gokongwei College of Engineering at De La Salle University. Her main research interests is the development of decision support tools for environmental decision making. She received her bachelor's degree in chemical engineering from the University of Philippines. She then completed her MSc degree in environmental engineering and management and earned her PhD degree in industrial engineering from De La Salle University, Philippines. She is the author of more than 300 Scopus Index publications and is among the world's top 2% scientists. She is currently an executive editor for the Journal of Cleaner Production, published by Elsevier, and an associate editor for Digital Chemical Engineering at the South African Journal of Chemical Engineering. Also, she is a part of editorial board of several other international journals published by Elsevier, Frontiers, and Springer Nature. She is the author of the book Input-Output Models for Sustainable Industrial Systems. For her scientific work, Professor Aviso has received multiple scientific awards from government and professional organizations in Philippines. Professor Aviso, the floor is yours.
Thank you so much, Natasha. And good morning, everyone. Thank you for joining us today on this very bright Sunday morning. Thank you for the organizers for giving me this opportunity to join this conference as one of your invited lecturers. So this morning, I just wanted to share with you some of the work that we've been doing at De La Salle University. And I've entitled it Process Systems Engineering for Integrated Carbon Management and Trading Networks, a Systems Pathway Towards Industrial Decarbonization. Okay. So just to briefly introduce our university. So De La Salle University is a private, comprehensive, non-stock, non-profit Catholic university, which was established in the year 1911. However, it was only in 1947 that we started providing engineering degrees, part of our effort to contribute towards nation building after World War II. Sorry, it moved. Okay, so we're proud that in the last 10, 15 years, we've managed to increase our research output by more than 700%, primarily driven as well by the very supportive administrative leadership that we have in the university. So just to show you where Manila is, so De La Salle University is in the heart of Manila, which is the capital of the Philippines. So I flew from Manila all the way here to Shenzhen with a stopover in Beijing, and then from Beijing to Shenzhen. So based on this map, it's about 1,000 kilometers away from where we are right now. So the two photos that you can see there on the right side is the front building of De La Salle University. It's our main building. It's the La Salle Hall. And then the one at the bottom features one of our newest buildings during Christmas time. So in the Philippines, Christmas is a very, very big occasion. I'm not sure if you've heard, but we're one of those who celebrate Christmas the longest. We begin celebrations in September. So there are other places in the Philippines. I hope you get a chance to come over. So we do have the urban area, the city, which is the Manila. And of course, we have a lot of beaches all around the country and the different islands of the archipelago. Okay, so now let's move on to the presentation. So this is just a brief outline of my presentation. So we'll go through decarbonization being a systems challenge, go through an overview of what the current state is and what we need to achieve in the next years so that we can keep global warming below the 2 degrees Celsius temperature increase. Then we'll discuss about process systems engineering as a means for analyzing decarbonization. Then the integration of markets and stakeholders as essential tools or perspectives when we deal with the problem about global warming. And then we'll end with some conclusions and recommendations. Okay. So as we've seen throughout this conference, we all know that climate change remains the most pressing environmental challenge of our time. We want to limit global temperature rise to well below 1.5 degrees, with the world needing net zero greenhouse gas emissions by 2050. So this is a threshold widely recognized to be critical so that we can avoid most severe and irreversible impacts of climate change. So however, the progress towards that goal remains uneven. So this figure comes from the Climate Action Tracker, which was last updated in October 25, showing us that only about 77% of global emissions are covered by national net zero pledges within countries' nationally determined contributions. And we know that recently the United States, who has previously pledged for the net zero pathway, has withdrawn from this commitment, and other countries still lack a clear or binding target. So the Philippines, as one of the countries, we do not really have a net zero pledge yet or a target. So we're one of those countries who have not yet joined towards this. So these gaps really highlight our urgent need for stronger international commitments and more coordinated strategies so that we can accelerate the transition towards a net zero future. So there are different ways or different pathways on how we can achieve this goal, but it will require coordinated implementation of the multiple strategies. So there is no single silver bullet. That's why we try to do anything that we can, try to find any technology or any strategy that can help us achieve this goal. So some strategies will include decarbonizing energy systems. We've seen a lot of that work in this conference. We want to adopt more renewable energy, improve energy efficiency. Other strategies push towards advancing circular economy practices so that we can be more efficient in the utilization of our resources. It will also be necessary to decarbonize hard-to-abate industries. So some sectors are more difficult to decarbonize. And because of that, we need to deploy carbon dioxide removal technologies or negative emissions technologies so that we can offset the emissions arising from this hard-to-abate technologies or sectors. So in addition, these need support in integrated systems planning, as well as enabling policy frameworks. So we can really push for the adoption of the different mechanisms that we have available. So the deployment of negative emission technologies is particularly critical for achieving net zero, like I mentioned, with hard-to-abate sectors such as cement manufacturing, aviation, and the shipping industry. So the complete elimination remains technically and economically challenging. So let me just borrow this illustration from IPCC, which shows us the different available compartments of carbon in our planet. So we need to have an understanding of where the carbon is and how carbon is actually utilized so that we can create strategies or mechanisms to capture this and manage them accordingly. So this illustration provides us with a good picture of how the different carbon dioxide removal technologies play a part in the carbon cycle. So one of the more popular carbon dioxide removal technology, a nature-based solution, is afforestation. I'm sure a lot of you are familiar with it. So essentially, it deals about creating new forests so that it can sequester carbon in vegetation or in oil or in soil. So essentially, we use the forest, the trees, so that they can take up more carbon dioxide from our atmosphere and store it as part of their biomass. We also have soil carbon sequestration, which means that carbon is stored in the live and dead soil biomass. So that's also another option for carbon dioxide removal. Blue carbon management is also being studied, which refers to the storage of carbon in live and dead marine biomass. Then we have biochar application, which is the sequestration of carbon in soil in the form of stable or carbon-rich biochar. So essentially, the biomass, the carbon in the biomass is not combusted completely, so it is not turned into carbon dioxide, and instead is transformed into biochar, which can be spread throughout our agricultural land. So this particular practice has been found to improve the conditions of the soil, which can yield additional benefits for agricultural crops. We also have enhanced weathering, which is the acceleration of the natural weathering process, wherein rocks are ground up and spread as well on land so that it can react with carbon dioxide in the atmosphere in the presence of water so that it becomes carbonates and then eventually flows into oceans and seas. Then we have ocean alkalinization, which promotes improving the ability of oceans to absorb carbon dioxide through pH adjustment. Then we have bioenergy with carbon capture and storage. So essentially what we want would be to replace some of the current conventional fossil fuels we're using for power generation, part of which can be generated using bioenergy, and then capture the emissions, and then eventually trap them into storage vessels such as geological reservoirs, which are available underneath. Direct air capture is the chemical or physical stripping of carbon dioxide from the air. So essentially, it just sucks up carbon dioxide from the atmosphere. And again, it will require some geological storage to keep carbon dioxide from returning back into the atmosphere. Then more recently, this has also emerged in the literature. It's called wood vaulting. So what you do is you bury the biomass and make sure that it's in anoxic conditions so that it prevents further decay, so that the material doesn't go back again into the atmosphere as your wood or your biomass decays. Okay. So these carbon dioxide removal technologies are at different levels of technology readiness, and their deployment are also at various levels. But we need to scale up the more novel negative emissions technology so they can be comparable with existing natural carbon dioxide sinks, so that we can have enough capacity to capture expected anthropogenic emissions. So this illustration just shows us the projected requirements of scale up for more novel CDRs compared with available natural carbon dioxide sinks at the moment. So in summary, the current state of carbon dioxide emissions and reductions are as follows. So based on literature, we need to remove 7 to 9 gigatons of carbon dioxide annually until 2050 so that we can keep global temperature rise to below 2 degrees or, if possible, 1.5 degrees Celsius. At the moment, only 2 gigatons of carbon dioxide are sequestered annually, mainly through conventional nature-based solutions such as afforestation and reforestation. But of course, there is also an emerging question about the permanence of these sequestration pathways, because that can sometimes be uncertain, and the vulnerability to reversal can be high. So decarbonization pathways can actually be tailored to reflect regional resource constraints and development priorities. We've seen in some studies that carbon dioxide removal technologies are not created equal, and it is not expected that all regions are to implement the same portfolio of technologies within their region. So we need to have a holistic understanding of the complex interactions among these technologies, our local conditions, the cultures that persist in that region, the possible trade-offs across economic, environmental, and even social performance of these technologies. And because of this, we need to address this challenge using a system-based approach so that we can capture the interdependencies and all the other factors that come into place so that we can have more informed decisions moving forward. So this is where process systems engineering comes into play. So I'd like to introduce you to process systems engineering. So it plays a critical role. It is a subfield of chemical engineering that focuses on analysis, design, optimization, and operation of systems involving physical, chemical, and biological processing operations. It is mainly characterized by its objective of being driven to understand the behavior of complex systems as a whole, with particular emphasis on how the individual components interact and collectively influence overall system performance. So process systems engineering as a field, when it evolved, was originally developed for the synthesis and design of chemical processes. However, throughout the years, its scope has expanded to encompass problems across multiple temporal and spatial scales. So in this illustration, you can see that there have been applications of process systems engineering at various scales and at various time scales. So today, PSE finds applications for micro, meso, and even at macro levels, ranging from the design of molecular structures and process control at plant level to enterprise planning, supply chain optimization, and even the management of large-scale industrial and global networks. So in addition to this temporal and spatial scale, we also need to integrate multidimensional sustainability considerations, such as accounting for economic and environmental indicators. And I guess one of the less explored would be social performance or social indicators, because it's still something that we cannot capture so clearly within our models. So we need this for system design as well as decision making. So here are just some of the tools that we are using for process systems engineering. We use mathematical programming, pitch analysis, heuristics, process graphs, and other allied methods to help us develop our models for analyzing and optimizing systems. Traditionally, the field was described to be deductive in nature, relying on general principles derived from fundamental chemical engineering science, physics, and mathematics. However, in recent years, especially with the growth in the ability to collect data and to process information, process system engineering is slowly, increasingly embracing data-driven approaches to complement the mechanistic models it initially used for its system design so that it can further enhance system understanding and decision-making. So in the field of decarbonization, as I've laid down, there are still significant knowledge gaps that we can explore, that needs to be addressed, and we intend to keep on looking at in our future modeling efforts. So these include managing uncertainties, which we all know is always present in our systems, especially when we are dealing with emerging technologies, when we don't really know how they will behave in the future or how they will perform. We also need to analyze systems over longer time horizons. The decarbonization problem needs to encompass centuries or millions or thousands of years ahead. So we need to evaluate multiple environmental footprints along with our carbon targets. So it's not enough to just look at carbon footprints or carbon dioxide reduction. We also want to look at the other environmental indicators that these solutions are bringing to the table. We need to develop holistic models that integrate the full range of available mechanisms and strategies needed to achieve our net zero targets. So this illustration just shows us some of the available carbon dioxide technologies and their resource requirements. So we need to take those into account. So even though they reduce or they remove carbon dioxide from the atmosphere, they also require additional resources to be implemented. Direct air capture requires substantial energy inputs, while bioenergy with carbon capture and storage places greater demands for land and water resources. As such, regions must carefully evaluate what is available in their immediate vicinity when determining which strategies are most appropriate or which ones to prioritize towards implementation. We need to look at cost uncertainties that can further complicate our decisions, account for temporal considerations. For example, how permanent will carbon be stored if we choose specific technologies? We need to ensure that carbon is removed from the atmosphere for hundreds and even thousands of years to make a difference. So carbon management, in addition, is inherently multi-stakeholder in nature. So we need to assess the different perspectives of our stakeholders so that we can design policies, strategies that will better adopt these technologies. Stakeholders can involve government, industry, and even communities with differing priorities as well as perspectives. So in PSE, these are just some of the models that we've tried to do, particularly to manage carbon. So essentially, we know that we have carbon sources, things that generate carbon. We need to manage them well, and so identify pathways of its utilization and eventually sequestration. So implementation of technologies involve global as well as regional cooperation. And selecting the optimal technology will require information from the immediate area where it's going to be implemented, as well as an understanding of the stakeholders that are at play. So essentially for carbon management networks, this is a very simplified illustration of how we can look at the problem. So essentially it's a source sink problem where we want to figure out the correct match between the different carbon sources and the different carbon sinks that are available. So this can actually be done using mixed integer linear programming, mathematical programming. So some of the work we've explored includes, for example, the integration of biomass co-firing networks and the production of biochar. So for this particular situation, we looked at how we can identify the power plants that would take in biomass for bio-co-firing, and then eventually determine where the product of biochar can be applied in the different land areas so that you can achieve the greatest carbon dioxide removal. So for this case, we looked at the indirect co-firing of biomass for biochar carbon sequestration. Another work has looked at the deployment of technologies to be conducted in phases, especially since not all technologies are already ready for deployment. So in this work, the model considers discount rates in carbon dioxide removal, as well as investment costs on negative emission technologies. And we found that cheaper, technologically ready options, such as afforestation and biochar, tend to be preferred and selected much earlier when doing the portfolio management, while more expensive and emerging technologies come much later in the implementation. So carbon value discounting and high initial carbon prices can also support early adoption of these technologies. We also wanted to look at using all the different strategies available to us. So it can be technology retrofits, it can be the use of carbon credits, and even implementing penalties when certain targets are not achieved. So in one of our works, we looked at data on different cement plants that were operating in Poland with identified baseline emissions and expected years of decommissioning, and looking at how or which particular plants should be retrofitted. Would they subscribe to carbon credits, or would they want to pay the penalties instead? And this was what our results found. So for that particular case study, we found that it's not necessary that all plants be retrofitted right away with the CCS technology, and some would would actually prefer to pay penalty costs instead, especially if they are cheaper. And later on, carbon credits were adopted instead. Okay. So in addition to mathematical programming, we've been using also the process graph framework, or P-graph framework, which was originally developed by Professor Friedler and Professor Fan. So it was initially developed for process network synthesis, and its main advantage includes computational efficiency and the automated generation of alternative network structures. At the moment, the most popular way of implementing P-graphs is through P-graph Studio. So it's available for download online. Yeah. So essentially, P-graph is a bipartite graph that utilizes M-type and O-type nodes. So M-type nodes represent materials, while O-type nodes represent processes. So one of its advantages is its ability to represent processes in an ambiguous way. So some examples are reflected here. But even though it was initially developed for process network synthesis, in the last year, it has found application for different fields as well. So P-graph actually maps well with a mixed integer linear program for process synthesis, as defined in this very simple model. And so when you map it out into the P-graph structure, the source sink model can actually be done in this way. So you can have sources represented by material nodes, such as this, while sinks are represented by product nodes, indicated here. And any requirements for quality constraints are also represented by hypothetical material nodes. The process nodes then reflect the flow of resources from sources and sinks. So within the P-graph framework, it works by utilizing the 5 different actions indicated here. So essentially, the intention is to be able to transform raw materials into the desired final product and identify the pathways it can take so that it can be transformed in that way. There is a means for integrating economic costs so that it will identify the most cost-efficient pathway from raw material to final product. Within the platform, or within the framework, has 3 different algorithms that works in the background. We have the maximal structure generator, which provides you with a rigorous way of generating the superstructure. So as long as you have identified all possible pathways from source to sink, it is able to generate that superstructure for you. Then we have the solution structure generator, which identifies all combinatorially feasible subset networks within the maximal structure. And then finally, we have the accelerated branch and bound, which provides an efficient way of identifying the optimal solution. So we've applied P-graph for carbon management as well. This is one example wherein we look at the availability of different energy sources and the requirements of different regions and the intention of reducing carbon emissions. So PGRAPH can be used for selecting the best portfolio of low carbon technology options while considering greenhouse gas reduction targets. In the same supply chain where we looked at co-firing networks and production of biochar for application, these can be also implemented in PGRAPH. And one of the advantages of PGRAPH is that it can readily provide you not just with an optimal solution, but other near optimal or alternative network structures that can later be evaluated by decision makers. So in summary, that PGRAPH framework enables rigorous network synthesis and has the ability to generate multiple alternative networks for efficient exploration of the decision makers. So it also allows the incorporation of various sustainability metrics and is not limited to process network synthesis. So you can actually combine sustainability metrics with the network design. So we've also looked at the influence of carbon markets and stakeholders into our models. So as we know, for any emission, any baseline emission, our systems try to look at the different strategies available so that we can arrive at maximum reductions that can be implemented. So in one of the work that we recently published, we tried to integrate carbon trading as part of that mechanism. So this is, again, just an illustration, just to visualize what it is about. So in this problem, carbon credits can be a strategy so that companies can meet their carbon reduction targets if they cannot adopt certain technologies to improve their performance. So the problem statement was stated in this way. So we have available carbon credit sources, and we have available external carbon source, maybe looking at what's available in the voluntary carbon markets, and trying to figure out, again, the matching between what is available, what is required by the different industries, and how and when these particular credits should be consumed or should be bought. So this is the mapping of our credit sources with the different demands. And again, in PGRAPH, it was able to identify different strategies for implementation of when carbon credits can be adopted. So it can be that one demand will utilize the external credits, or it can be distributed across the different requiring industries. So what are the implications? It enables businesses to reconsider decisions, actually have an understanding of when they should buy these carbon credits. It also helps early and informed actions and facilitates the development of a trading policy. So it provides insights as well on network robustness that may be essential for developing contingency measures, especially if we want to make sure that carbon reduction is done for longer periods of time. The next thing that I'd like to discuss is how we've integrated different perspectives of our stakeholders. So we've utilized game theory to align stakeholder alignment. So essentially, it helps us in understanding the roles of the various stakeholders, their interests, and it can help us align between individual as well as collective interests so that we can develop effective strategies that will encourage industry or the government to implement the adoption of technologies. So what exactly is game theory? So game theory provides a framework for analyzing interactions among multiple rational agents, especially when decisions are made under potentially conflicting interests. So often, it is referred to as the science of strategy or the mathematics of decision making. So it studies how each agent or player in the system should select actions so that they can maximize their own benefit while considering the actions and constraints imposed by others. So game theory is actually divided into two different classes. We have the cooperative games and the non-cooperative games. So for cooperative games, there tends to be more coordination between the players in the system. But often, what we experience are non-cooperative games, which is a class of games where players can take unilateral decisions, which means that there is no prior agreement between the parties involved. So the decision makers can just change their decisions without even considering what the other player wants to decide on. Some of the popular games, non-cooperative games, include the Nash equilibrium and the Stackelberg solution to be examples for this one. So these two actually differ also based on the capability of players to anticipate others' actions. So for a Nash game, typically you assume that the players in the game would have the same power or ability to make a decision. However, there is a certain class of games called Stackelberg games, which takes into account the possibility of a hierarchical structure between the decision makers. So the Stackelberg game is also known as the leader-follower game. It is a non-cooperative game which occurs in situations when one player can be designated as the leader, such that the leader has the capability of anticipating the reaction of the follower. So the leader usually has complete knowledge of the follower's problem, such that the follower can only react based on the action made by the leader. So the leader is able to strategize to take an action which will induce the desired reaction from the follower. So maybe you can liken this into like a chess match wherein an expert is playing with a novice player. So an expert would already anticipate ahead of time what the novice player will probably do given certain reactions that it puts into play. So the Stackelberg game can actually be modeled as a bi-level mathematical program characterized by its hierarchical structure, wherein you have the upper level problem representing the leader's objective and a lower level problem represented by the follower's response. So in mathematical programming, this is an optimization problem wherein you have nested inner optimization problem such that are constrained by the outer model. So this structure can be seen in various real-world problems, such as when governments develop policies to induce behavior and private agents towards achieving national goals. So the model has been successfully used for fields such as economics, logistics, computer science, and even in the defense of critical infrastructure. So the bi-level model can be represented by this generic mathematical program. So as you can see, we have the outer optimization problem, which represents the leader's objective, which is influenced by both the leader and the follower's decision. So the subscript 1 represents the leader's variable, while subscript 2 represents those of the follower. So the upper level problem is further constrained by inequality conditions that are relevant to the leader. And of course, it depends. The exact formulation will depend on the problem that we're trying to solve. The follower's optimization is nested within the leader's problem, wherein the decision variables of the leader become parameters for our follower. So once the leader already makes a decision based on its decision variables, these variables are taken as constants or parameters within the follower's objective function. So each player has direct control only on some variables of the problem. So some of the work we've done is applying this construct or this framework in the selection of negative emissions technologies. So we can visualize the hierarchical nature of the decision making using this illustration, where you have the leader on top, represented by the government, who selects which particular technology will be implemented. Now, these technologies are further characterized by their performance in different attributes, such as their ability to sequester carbon dioxide, their need for energy, their water footprint, and maybe even cost. In this model, we looked at public acceptance as well. However, public acceptance becomes variable. It varies depending on how well the follower takes that particular technology. So it is determined later on depending on the performance of the follower. So the follower would have its own objective, again, evaluating different technologies based on different attributes. So the two may have different objectives. The leader might be after reducing carbon emissions, but the follower might be after reducing economic costs. So just to give an illustration, so these were the different carbon dioxide removal technologies we used using the different criteria indicated there on the lower right. So at the beginning, if no strategy was ever implemented, the preference of the leader would be quite different to the follower when you evaluate each technology based on the different criteria. However, it is possible for the government to implement certain types of policies. For example, providing subsidies on technologies so they will appear less costly for our followers or for the industry. So when that was taken into account, there was a shift in the preference ranking of the follower, such as in the end, both leader and follower ended up with the same technology selection. So we also use this for looking at optimizing carbon dioxide removal portfolios. Again, with the government as the leader, trying to maximize decarbonization public benefit, and the followers trying to minimize total cost. The costs are associated with their implementation of CDR technology, as well as the possible penalties that can then be asked from them if they are not able to meet their target. So for the leader, it tries to select the total carbon dioxide removal that the entire system should have. And then it selects a level for durable CDR. So since not all CDR are created equal, certain types of carbon dioxide removal are more durable in the sense that you can expect sequestration for longer periods of time. So the leader seeks to maximize the total monetized public benefit for decarbonization, taking into consideration the social cost of carbon. So for the follower, it selects actual emissions cuts, selects CDR technologies to implement, and seeks to minimize the total cost for the industry. So we implemented this using a grid search algorithm while combining the two objective functions into a single objective function represented here. However, it is an iterative way of looking for the solution as illustrated in this flow chart. And so we stop once a common solution is established by both the leader and the follower. So this is a summary of the results. So if it was just the leader that was followed, if it was just the leader optimizing everything, the results can be found in the second column. Here, the leader would select the implementation of biochar as well as direct air capture. If it was all up to the follower, they would select afforestation and reforestation as this was the cheapest option, as well as enhanced weathering. Now, by implementing certain penalties or certain subsidies, it is possible to arrive at a Stackelberg solution where the leader can convince the follower to actually utilize enhanced weathering, which is a more durable form of carbon dioxide removal. So those are just some examples of how we've integrated stakeholder perspectives into our models. Okay, and then to summarize, so we need an integrated systems pathway towards developing decarbonization strategies. So these need to look at technology and infrastructure integration, such that the deployment of carbon capture, utilization, storage, renewable energy, and hydrogen systems across industrial processes are accounted for. So network design and optimization can be implemented through the use of P-graph methodologies, mathematical optimization, to enable systematic synthesis of carbon management and resource exchange networks. So strategic and market interactions should be included in the models. So Stackelberg games can be one form of that integration, which captures the strategic behavior of regulators, market operators, as well as firms and carbon trading systems. So policy and market mechanisms should be included as well, wherein you look at carbon pricing, emissions trading, and other available regulatory frameworks that can help incentivize low carbon transitions. Finally, we need to account for sustainability dimensions. This integrated decision-making should consider economic, environmental, as well as social implications whenever we identify decarbonization strategies. So in summary, industrial decarbonization is a systems problem. P-graph can help us, or mathematical models can help us synthesize these carbon management networks. We need to integrate solutions that account for the different perspectives. And towards the future, we can look at developing more data-driven, integrated, and cooperative carbon management systems that can help connect industry, policy, as well as technology. So with that, I'd like to end my presentation, and I'd be happy to welcome any questions. Thank you.
Thank you also for bringing on board this industrial decarbonization as a very important topic, and offering technology solutions, but also analytical framework to analyze this very important topic. Now I would like to invite the audience for some questions. Yes, Neven, please.
Thank you for very comprehensive talk. All these frameworks count implicitly on huge fossil fuel storages. So the time of use of energy is not important. But we are moving slowly to electrified economy, electrified industries. This framework has to be tweaked significantly in order to take into account that. I remember Robin Smith's lecture in Dubrovnik some 10 years ago, where he tried to do that. And it's not that easy. So this is my first question. How do you plan to integrate time of use aspect of electricity? And the other thing is, we are moving, not yet, but we see it on the horizon, to methanol economy, especially in chemical industry. How do you see that being incorporated into your framework?
Thank you so much, Neven. Yes, I totally agree that we're seeing more and more developments as we progress towards decarbonizing the industry as well as other sectors of our economy. So with regards to integrating the use of electricity, I think we really need to have a more multi-period analysis, so we can see how the current systems can be slowly phased out and eventually new systems are coming into play. So yes, there's still a lot of work that should be done. And for with methanol economy, yes, I think this really is a critical part, especially when it comes to decarbonizing the chemical industry, because I've actually read that some people say that it might be impossible to fully decarbonize the chemical industry, since it has a lot of materials that are based on carbon. So yeah, so I think we should look also at how this the flow of molecules are within the system and see where they actually end up in.
Okay, thank you. I saw a question over there.
Thank you for this nice presentation. I have just a curiosity on the last results and why direct air capture achieves so high score. Because according to the overall, according to my understanding, is a very low efficiency strategy for capturing CO2. So there are other strategies that can better exploit the energy used for capturing CO2. Another point is that sometimes I found that people does not take into account the energy needed for capturing CO2.
Yes,
this means that 1 kilograms of equivalent CO2 captured means that the effectiveness is less than 1, is because you are going to consume some energy that now unfortunately is not fully renewable. Thank you.
Okay, thank you. Are you talking about this slide?
Yeah.
Okay, yeah. Okay, so for this one, yeah, it is actually for the leader solution. So for the leader, it is like an iron hand saying that we want to capture more. So for the leader, it was more of identifying technologies that can have more durable carbon dioxide sequestration. But you're correct. Yeah, that's why it's a very, very complex problem. We have to take those into account. And with regards to, yeah, some the society maybe not considering the energy requirement for other for the implementation of certain technologies. So we can also develop the our equations so that we can take those into account. Thank you.
Thank you so much for your presentation. My name is Bemi. I'm an associate professor of market-based mechanisms at Imperial College. It was very good to see market-based mechanisms in your slides. I also have a process systems engineering background, BSc, bachelor's and PhD. Now, I have been focusing on market-based mechanisms. So today around the world, you have about 13 types that leads to over 20,000 interventions that affect all industrial sectors, and they trade globally. Right, so you're looking at maybe about 6,000 industry regulated entities that all have to make a decision at the same time, driven by these market-based mechanisms. Are you confident that the Stackelberg can work for it? Because we've tried all systems engineering to capture at the same time that global interactions, because governments are moving very fast. Industry is moving very slow, and all of a sudden they wake up and they are faced with a high tax bill that's either coming from CBAM or the IMO or COSIA that affects them. I mean, I'll be very happy to collaborate with you on the future direction to see if we can capture that interaction with any of our PSC tools. Thank you again for your presentation.
Yes, thank you. We should discuss. Thank you.
Since we were on interactions, I would like to ask, yesterday we had an excellent presentation on urban mitigation actions, and maybe we also are witnessing a lot of push, like example for the cities of Barcelona or Copenhagen on this symbiosis on industrial decarbonization and urban mobility. So maybe your take on how this can be integrated and like a governance to connect these two areas for mitigation. For example, tackling some areas like waste heat utilization, or resource circularities flows, or some shared infrastructure.
Thank you. That's a very, very good proposal. I think we should work towards that, towards integrating the different things that we're working on. Actually, truthfully, for our group, we have not explored urban mitigation, and we haven't really looked into that area yet. But you're right. It's something that we need to connect, since everything really interacts with each other.
Thank you very much. We still have some time for questions. Yes.
Thank you for the comprehensive discussion. I was very much interested, and I track your work with Raymond on this, on the negative emissions technologies. Can you elaborate which technologies you think are most beneficial to reduce greenhouse gas effects?
Yeah, so actually it really depends on where you intend to implement the negative emissions technologies. So it will depend on what are the available resources. Maybe in our region, in the Philippines, maybe would be more inclined towards enhanced weathering, especially since its technology readiness level, it can be more easily deployed in our region. But maybe elsewhere, for example, there are regions that have more capacity to store carbon dioxide underground, then there might be better BECCS and DAC might be the way to go.
Okay, thank you, Kathleen. I think this is a good point to conclude this session. Thank you very much for very insightful presentation. Also, thank you. Thanks to the audience for all the contributions. We can, of course, continue the conversation over the coffee break.
Thank you.
Thank you very much. We close the session.